All right, so I'd like to welcome you to MITEI Presents, the Energy Transition. And today's speaker is Professor Emily Carter from Princeton University. Professor Carter was a famous kind of computational quantum chemist for many years, published more than, probably around 500 papers, I don't know, something like that. Quite a lot of journal papers. Some of her students have been extremely successful professors as well. But in maybe 10, 15 years ago, she started working heavily in energy as well, not just in kind of computational methods, but also bigger macro energy problems, and became the founding director of the Endlinger Center, Energy Center at Princeton. And she got that off to a great start. So she did so well in that job that they decided to hire her to be Dean of Engineering at Princeton. And even though she was not originally trained to be an engineer, I don't think. And then she did so well at that job that she got hired to be the provost at UCLA. A few years ago, Professor Carter came back to Princeton, where she is today. She's professor in mechanical and aerospace engineering department. She's also in the Endlinger Center, for energy and the environment, and also in applied and computational mathematics. And she's also, at Princeton, there's a small national lab called the Princeton Plasma Physics Lab, one of the most important labs for fusion research in our country. And she's on the management team of that national lab as well. She has quite an impressively long list of accomplishments and awards. In particular, she's a member of the National Academy, and she's also a member of the Royal Society in England. And she also is the National Academy of Inventors as well. Is that right? Yeah. But today she's going to talk about a really challenging problem that we all face is how to proceed. The energy transition has apparently not been as fast as we were hoping. And so we have to consider all kinds of other angles. And so today she's going to talk about that major challenge ahead. So Professor Carter.
Well, thank you for being here. Thank you, Bill, for the introduction. And I will say that Bill had invited me to come to talk to you about the energy transition and my take on it. And so you see what my title was. It's The Energy Transition is Not Enough. Because I will say, Bill alluded to the fact that I've been working in the space of energy research for quite some time and more recently policy. But, for me, it actually started 18 years ago when I don't know why, but I happened to read the part of, not the entire thing by any means, but part of the Intergovernmental Panel on Climate Change science report in 2007, which made it clear at the 95% confidence level that human beings were causing the world to warm through the burning of fossil fuels. And so for me as a scientist / engineer, we're all problem solvers. And so I had to think about, I immediately started thinking about how I might apply my own skill set to doing research in the area of sustainable energy in particular. And I think, a lot of people have been called to that and have been working on that for a long time. And we see, of course, that much of the transition is certainly not finished, but there are many solutions already in the energy space where there are much more, and there are challenges in the energy transition itself, but I believe that we can't, given where we are today, and I think presumably all of us have witnessed what climate change is already inducing on the planet in terms of severe weather of all kinds, we have to be thinking beyond just changing how we produce energy. And so that's why the title of the talk is The Energy Transition is No Longer Enough, Transformation, Intervention, and Adaptation. And those words can be interpreted in many ways, and so I'm just going to give you my take, of course, on those words. And I will say that 18 years ago when I had this epiphany, I pivoted all of my research into work on sustainable energy, and more recently my research has been focused on things that largely fall under the term carbon mitigation. And so I continue to do that kind of work, but as was mentioned, I've been taking various leadership roles because I've felt that while I can continue to do research and mentor the next generation of students and early career folks working in this space, I think it is also important to, when you get to a certain point in your career, to give back in different ways. And one way is through various leadership roles. And so, as Bill mentioned, I wear a lot of hats, and I thought I would just say a couple of things about the different kinds of hats I'm wearing, in addition to being a professor. Right now, as Bill mentioned, I'm helping lead the Princeton Plasma Physics Lab, which is the national lab. It's a Department of Energy national lab focused on fusion energy, and I was asked to come back and help the lab diversify its research portfolio into sustainability science beyond fusion energy. So things that might take advantage of the last administration's focus on climate change mitigation. And this is something that really drives me, is very important to me, and so I agreed to come back to do this work for the National Lab and for the Department of Energy and for Princeton. So in addition to that leadership role, where I'm a senior strategic advisor and associate lab director, I also was approached by the national academies to lead, and I finished last fall, leading a 3-year congressionally mandated study on carbon utilization, both carbon dioxide utilization, but also what we might do with coal waste. And so I will touch on that a little bit, because I think that experience of working with a really diverse group of experts to bring these reports to fruition, in particular to help, we delivered 2 reports, and the first one was really focused on markets and infrastructure, which was important under the last administration because there were, as you were probably aware, bipartisan laws that were passed to invest in such infrastructure, and we wanted to be able to inform those decisions about such infrastructure. In addition, I serve on various advisory boards, and in particular, for this particular discussion, I also am working as a consultant for the Simons Foundation, which is a foundation that supports basic science. And when it was announced that I was going to be coming back to lead this effort at the DOE National Lab, the new president of the Simons Foundation actually approached me about working with them on a topic that I had decided that the Princeton Plasma Physics Lab should get involved in. I hoped that they would get involved in. I hoped I would convince people at the laboratory that this was something that they could in fact contribute to, and that is a climate intervention strategy that's known as solar geoengineering. That's a term that's now gone out of fashion. We now call it solar radiation management or solar radiation modification. They both go by the name SRM, so that's convenient. And so I'm going to talk about that with respect to intervention, because I have essentially helped the Simons Foundation launch major international collaboration of a bunch of teams that are working on the basic science associated with that particular strategy that has to do with essentially producing a Band-Aid for the planet. It's not a permanent solution, but a Band-Aid to help modulate the surface temperature, potentially, the Earth's global temperature. So we'll talk about that a little bit. And then the other role that I play, I mean, there are others, but the other one that's relevant for this is after I finished the work with the National Academies, during which time I was very careful to deconflict myself from everything that could possibly be questioned, because I felt that this work was so important. I wanted to make sure that I was completely pristine individual with respect to any potential conflicts of interest. But after that work was finished, I decided to agree to chair a scientific advisory board for a startup that is working on what I think is a promising technology for what's called direct ocean capture of CO2. So it's a possible means of carbon dioxide removal from the atmosphere, which is going to be a very important part of our future. So that's part of intervention, but if you like, it's also a transformation of our environment and of our industrial system. So those are the kinds of hats I wear. I haven't named all of them, but that's to give you some sense of an introduction to where I'm coming from. So now I'm going to make a statement, and that is that the future, our future on this planet, it's funny, I'll say one thing before I finish the statement, which is I used to give talks where I would say, how to solve the world's energy problems, and sometimes I would glibly say, and save the planet, okay? I would urge you to stop saying that I urge myself to stop saying that, and I'd urge you to stop saying that because the planet will be fine, okay? The planet has endured much worse than us over its $4.5 billion year existence. So we're just this perturbation. We're annoying it, but we're basically a perturbation on what the planet can live through. But we can't live through it if we don't start to do something about it. So it's really about saving life on Earth. And I spent a couple of days with philosophers talking about the ethics of solar geoengineering, and came away learning. I always learn from new perspectives, and I came away realizing that in general we are very human-centric. We talk about saving humanity, and I think, and even Princeton has as part of its motto, Princeton in the nation's service and in the service of humanity. The ethicists at this gathering pointed out that there isn't just human life on Earth, right? So now I say let's do our best to preserve life on Earth, because that includes the animals and the plants and the microbes, and I think we should be thinking of them and not just human beings. So given that, our sustainable future for life in general on the planet, we have to be thinking about both how we recover from past activities, namely the century and a half of burning oil and natural gas, and before that coal, and how we transition to a zero to negative greenhouse gas emission civilization. We have to do both recover from what we've done in the past, and if all we do is take care of what we did in the past, but we don't change what we do, so the adaptation, the transformation, then we're still going to be left with very serious problems with respect to climate change. So with that, how do we move forward? Well, the energy transition deals with one aspect of it, and that is the transition to carbon emission-free electricity. And that's a very important piece of it, and it's what people call, I always laugh, people talk about decarbonization. We have to decarbonize our future. A decarbonized future would mean we were all dead, right? We're made of carbon. So, and food is made of carbon. And so what we mean by that really is the decarbonization of the electricity system. That is the piece that can be decarbonized, and in fact already is partially decarbonized, of course, with the increase in use of solar and wind, which is still not a major factor yet. It's growing, but it's not a major factor in terms of the entire energy electricity landscape. But nuclear, hydropower, a little bit of geothermal. What is on the horizon for carbon emission-free electricity? Actually, the new Secretary of Energy, who I understand has a degree from MIT, is very interested in advanced geothermal. I think he's right about that. If we can figure out how to do it without inducing earthquakes, so we need to do science associated with understanding the level of seismicity and how to minimize that. I think there's some really interesting science problems there. And then, of course, fusion. And fusion to replace nuclear eventually, and advanced nuclear. But we already have nuclear, so I didn't really want to mention it separately. But in terms of new technologies coming on, I think those are very likely in the second half. Advanced geothermal may come on in the next couple of decades. Fusion will only really start to play a role, later on in this century, but could provide firm electricity such that we could start to decommission nuclear, because fusion has the potential to have much less problems than nuclear in terms of waste issues, for example, and safety. So there's carbon-free electricity, which is critical. And then we should be using that carbon-free electricity to electrify everything we can. We already see electric vehicles, so electrification of transport for where it can be electrified. Obviously, electrification of buildings, that already exists. The part that I saw as a key area for researchers that I brought the idea to the Princeton Plasma Physics Lab is to electrify industry. And in particular, and so we started an initiative at the Princeton Plasma Physics Lab called Electromanufacturing Science. And the point is that so what is the idea? The idea is that ultimately, the energy transition is about transitioning off of fossil fuels. But if you look at the manufacturing industries, they are driven by fossil fuels right now. They are driven by fossil fuel-driven thermal processes, using heat. Of course, we know as engineers that heat is not the most efficient form of energy. Electricity is much more efficient. So in principle, we can imagine replacing those fossil fuel-driven thermal processes with electricity-driven processes. Either electricity to do straight electrolysis, okay, so electrochemistry, electrosynthesis, and of course, industry already uses that. For example, we know we can do it because we use electrolysis, for example, to make aluminum, okay, in mass quantities. So we know that that's possible. So electrolysis is the obvious one. Maybe less obvious is to use electricity to create plasmas. The beautiful thing about plasmas is it's a very interesting, tunable source of both electrons and ions, that if you have a low temperature plasma, you may be able to gently synthesize and manufacture, not just as we do now, all of microelectronics chips, where half of the steps in microelectronics use plasmas, but also to synthesize chemicals, to synthesize other kinds of materials. And so that's where the Princeton Plasma Physics Lab comes into play. Electrolysis. Also, one can use, for example, LEDs. So electricity to generate light through using LEDs, to then do photocatalysis, to do photo-generated synthesis. That's another then form of doing of using electricity, but to do them not from sunlight directly, but from LEDs. And there are companies that are doing this right now to do photocatalysis. I'm not involved with a company. I'm not involved with a company that's doing this, but I'm involved with the founders doing basic research in this area. In addition, last one, so I've named 3 electromanufacturing strategies. The fourth one is you can use electricity to do what's called joule heating, basically doing resistive heating. And essentially the beauty of that, rather than using fossil fuels, first of all, you're not using fossil fuels if you're using clean electricity, carbon-free electricity. But in addition, you could imagine playing with pulsing the electricity, turning it on and off at different rates, different ramp rates, in ways that could conserve energy, use less energy, and perhaps open up, and this is another project I'm involved with a group of people that's funded by the Department of Energy, to see if we can use this joule heating, for example, to synthesize ammonia instead of doing the Haber-Bosch process, which is so energy intensive. So those are just some examples of the ways in which one can think about using electricity to transform the industrial sector. We've talked about electricity. The other point, though, is I mentioned using electricity for transportation. While I heard once a talk by somebody high up in Boeing talking about what does their transformation journey look like. And while you can imagine electrifying small planes, you are not going to electrify the very long-range aircraft and heavy-duty aircraft. You're not going to electrify, even though there are electric boats, you're not going to electrify aircraft carrier. Well, they are actually through nuclear reactors, so bad choice. But many ships, right, which use diesel fuel, many of them, it's not going to make sense it's definitely not going to make sense to put a nuclear reactor on them. It's also not going to make sense to weigh them down with batteries. And so there are parts of the transportation sector that involve heavy-duty transportation, which will still need fuels, no matter what. And so there's a lot of talk about sustainable aviation fuels. So that is one area that could involve, for example, either from plants or from carbon dioxide that comes from a clean source that gets converted, for example, by microbes to jet fuel. And there's a company that is working on that today. So, I mean, I'm sure there are multiple companies. I know in particular of one that has made a lot of progress in that regard. So carbon neutral fuels for aviation, for heavy duty aviation and shipping, it's going to be very important. That'll be part of the circular economy. Has to be part of the circular carbon economy because we know that when we burn those fuels, they're going to produce CO2 again. So they need to come from from a source of CO2 that is not fossil based, because if it's fossil based, then you're emitting more to the atmosphere. So that's one point. I will also say that in addition to carbon neutral fuels, the next thing that we have to be thinking about, so that's part of the transformation, is intervention. And the best intervention, in my mind, is carbon dioxide removal. Why? Because it's much less risky than the solar geoengineering that I'm going to talk about in a moment. So the carbon dioxide removal, why is it less risky? Because all it's doing is taking our present state and going back to a past state where things were fine, right? And we're removing the pollutant. We're not introducing possible new pollutants that we don't know what will happen upon their. We won't know all of the knockoff effects if we introduce some other substance into the atmosphere. So removal is very important, and so that carbon dioxide removal necessitates work on and build out of CO2 capture, utilization, which is what this National Academy study that I chaired, that I mentioned before. So carbon capture, utilization, and storage. So the estimates from our National Academy's report were that by mid-century, we might be able to, not saying we will, but we might be able to utilize up to a few gigatons of CO2 per year in processes that lead to chemicals and materials that we need. That's not very much because we're putting into the atmosphere right now about 40 gigatons per year. And there's a lot of buildup. Estimates are of the order of 2,000 gigatons that needs to be potentially removed. Large parts of it need to be removed. So that requires that we have to be thinking about storage. And there's a lot of talk about building large numbers of pipelines to capture the CO2 from, for example, fossil fuel-driven power plants, from cement plants, from steel plants, from all sorts of industrial places that emit CO2, and then piping it and then storing it in underground aquifers. We will need to do something. It remains to be seen whether or not we will actually build out such pipelines. There's a lot of issues associated with how we convince the public that we can do that responsibly and safely. And so I can tell you that Europe has already voted with their feet. They are not doing carbon capture and sequestration on land. The only place where it is going to happen is offshore, much more expensive, but that's what's going to happen. And it may be that that's what we end up doing as well. So there's a lot of costs, and one may think, you know, why are we're storing this underground? Why would anybody pay to do that? You have to think about this as just like we pick up garbage. This is a waste. This is a waste disposal problem, and this is what we have to do as a public good, just like we pick up garbage. So that has to happen. But another thing that can be done to sort of help that process along is utilization. So if we can make valuable products, even at the few gigatons per year, that may help accelerate doing carbon sequestration. The other way, though, that we can think about doing sequestration is not just pumping gaseous or supercritical CO2 underground, offshore probably, but we can also be thinking about converting it directly through a process called mineralization, where we can take CO2 and react it with some alkaline material or a source of alkali, such that we convert it to carbonates. And then basically we could use those carbonates. Those metal carbonates can be used, for example, as building materials. They can be used to form concrete. They can be used as road paving materials. So there are many ways in which it could be used, and also they can just be stored, for example, in the ocean. So that's another avenue to CCS, to what has to happen, and that is part of the transformation that's going to happen of our industrial systems, and also it is a form of intervention. And then finally, beyond carbon dioxide removal and carbon dioxide and carbon in general, waste carbon utilization, because I should say, I'm not standing up here, you know, waving the flag necessarily for CO2 being the feedstock. It has to prove itself. It may be a useful feedstock. It already is being used, for example, to make urea, a fertilizer, and it's being used in certain areas. But there will be, for example, waste plastics, biomass waste, where the carbon from those may turn out to be the better way to make the products that involve carbon in the future. We'll see. They will all have to compete with one another. And then finally, there's this, and then I think I will stop. The issue of intervention that I mentioned, this solar radiation management or solar geoengineering. And I view that as a last resort. I do think, and that's why I've been leading for the Simons Foundation, co-leading with some subject matter experts that are much more expert than I, a set of projects that have to do with understanding the physical and chemical properties of aerosols. So let me explain very briefly what the solar geoengineering is. It is the idea that you might inject. These are the three main strategies. There are others. You might inject into the stratosphere some particles that will reflect sunlight to help cool the Earth. Where would this idea come from? We have natural experiments that show it works. There have been volcanic eruptions. In particular, one spectacular case is that of Mount Pinatubo from 1991, where measurements were made after that volcano erupted and spewed sulfur dioxide up into the stratosphere, where it made sulfuric acid / sulfates, and it turned out that those sulfates spread, those sulfate aerosols spread worldwide in the stratosphere, and they cooled the Earth by about 0.5 degrees Celsius for more than a year. So we know that sulfate aerosols can do that. A lot of people are talking about using sulfate. I view that as a sort of a failure of imagination. I don't think that sulfate is necessarily the best possible choice. It may be the only choice, but we need to understand. And there are a number of aerosol engineers and scientists who are working on looking at other possible aerosols that might have, for example, less effect on ozone. That's a huge concern with the sulfates. you're aware that we need a layer of ozone to protect us all from skin cancer, for example. And so we need to make sure that whatever we think about using up there, if it's in the stratosphere, there are other strategies for what's called the upper troposphere, called cirrus cloud thinning. That's much less understood. We're also funding some work to understand that phenomenon. And then there's another set of people that are looking at something called marine cloud brightening, and that's much closer to the Earth. It's just clouds over the ocean. Those clouds, that would be for possible regional effects, where people are thinking about spraying sea salt and brightening those clouds so that they can reflect more light. The cirrus cloud thinning has to do with making the clouds thin enough to let more infrared radiation, so heat from the Earth, back out into space. So those are the three main processes. And my view is, I hope we don't ever have to do it, but I sure think we should understand what would happen in case somebody else just decides to do it. It's a national security issue. It's a global security issue, and it is definitely a national security issue that we need to understand that if someone decided to go try to do that intervention, because in principle it's not so difficult technologically, we'd like to really understand and be able to predict what would happen if that happened. And we don't understand the science well enough to know. So that scares me, and it scares a lot of people. And so we need to do the science to do it, and that's what we're trying to do with the Simons Administration, Simons Foundation. So very last, and we can talk more about this together, is we've talked about a lot of need for research in various areas and deployment of different technologies. The fact is that we often talk as scientists and engineers that, something invented in a university, to make it to a product, there's the valley of death, that where ideas go to die because they don't somehow make it for various reasons. There's another valley of death that often doesn't get talked about, and that in this report, the National Academy's reports, we did talk about, which is that you could have the best technology, you could have it fully developed, ready to deploy, and if you haven't done a good job with stakeholder engagement, with community engagement, to be able to listen to people's concerns and address those concerns, the technology will never get deployed. So it's extremely important that we deal with those issues as well early, way early, and make sure that stakeholders are engaged from once it's clear that there's a possible deployment. We need to start those conversations and make sure that people feel comfortable and that those concerns are addressed and taken very respectfully into consideration as those things are deployed. So with that, I hope I've given enough food for thought for a discussion. Thank you.
Thank you very much. You can come over, we can have a chat. So thank you very much. That was very interesting. I was particularly struck by your last comments about the stakeholder engagement. We here in the Energy Initiative, we engage a lot with the companies that are stakeholders, as well as with the students and the researchers who are stakeholders too. Maybe I was wondering if you could tell some stories or your thoughts about stakeholder engagement, because it's many people have stakes in this. I mean, in fact, all of us have a stake in what happens with the climate.
Yeah, so I'll give you one example, just a personal story. I went to visit my parents who used to live in Central California. And there was a flyer at some coffee shop I went into. And the flyer said, I don't remember what the date was, come protest smart meters. Smart meters are bad. They're an invasion of privacy, et cetera, et cetera. And I thought it was a perfect example of PG&E, they've made their share of mistakes along the way, as they know. They did not do a good enough job to engage people to explain that they, presumably, I don't know, I'm not an employee of PG&E, but I assume they anonymize the data. There's not an invasion of privacy, and it offers up the opportunity to load balance, the electricity needs, and to save the consumer money. It's only a win-win. So I think that's like a perfect example of, not having spent the time to do that properly. Okay.
And I guess this gets to issues of public trust and maybe
Yes.
public level of critical thinking and understanding of things. I don't know if maybe you have some thoughts. Both of us are in education, and I feel like maybe we've let the country down by the way I see how things are going. Maybe we really didn't do such a good job at educating people, but I don't know.
Well, I think that one of the things I've learned in a lot of the different roles that I've had is that it's super important to listen and be humble and be respectful of people who, yes, they may not have the expert knowledge. Most people wouldn't have the expert knowledge, but they are right to have fears. I mean, I'll give another example. Just a few years ago, there was, mostly the CO2 pipelines. We have 5,000 miles of CO2 pipelines in the United States. You may not know that. We need many thousands more if we're going to do the CCS the way it's potentially envisioned, carbon capture and sequestration. But there was a rupture of a pipeline, and a few years ago. And what I will say is that so generally speaking, great safety record overall. Mostly those CO2 pipelines, by the way, have been used for what's called EOR, enhanced oil recovery. So they're all around the Gulf region. And anyway, the point is that there was this rupture. The community had no idea there was a pipeline there. Luckily, no one died. I mean, CO2 is an asphyxiant. It's heavier than air, so it comes down to the ground level. About 45 people went to the hospital. So it was, I think there is a lack, what is really lacking is the lack of conversation and transparency. And that, I think, is what is needed for people to be able to voice their fears, their right to have fears, and hopefully there's enough information given to assuage their fears, but we have to gain the trust of people. And frankly, I think the best way to do that is to be going to communities and finding someone who is curious about technology and wants to learn about it, and to bring them in to talk about the technology and have them be able to be, if you like, the interpreter to their community who trusts them. That came up a lot, actually, in discussions we had when we were researching for the report about policy issues, that you need to find trusted intermediaries.
That's really key. Another whole angle in this is that before you would go to the public to talk about a new technology or a new way to try to modify the climate, the engineers would have to be convinced, the scientists would have to be convinced it's actually a good idea. And I've noticed that that's often difficult to achieve as well. You must have also run into this. Maybe you have some stories about that, or?
Well, I think that's one of the beauties of the scientific community, is that we're all here to critique each other. And hopefully we do it in a humane way. It doesn't always happen that way. I'm sure you all know that. But it should, I don't have a problem with that. I think that skepticism is good. You should have to prove your proof of principle. And in fact, there are many cases where people, I would say, have overpromised on a technology and said, oh, I've solved that problem. And that can be very, in fact, I remember being extremely frustrated with a person who, shall we remain nameless, who told the press that he had solved the problem of let's say, of artificial photosynthesis, okay? And what that does, first of all, then people think, oh, he solved the problem. That's great. Where is it? Where's the solution? But it hasn't been deployed, right? Because it hadn't really been solved. From the scientist's point of view, that's really bad because it hurts one scientist. Overpromising hurts all scientists' credibility. It's not that one scientist that gets blamed. So it's extremely important for us to be totally transparent and talk about the limitations, talk about the pros and cons, so that people can trust what you say.
And I have to say, I've run into the same issue as a fellow scientist in the same specialty. And one person in the specialty tells a baloney story. And not only does it make nobody trust work in this area anymore, when they find it doesn't work, while they still believe the baloney story, it cuts off all the funding because all the funding agencies say, oh, you solved the problem. Why are we funding anybody working this problem anymore?
Right.
And so it kills off all the rest of the people in the field
right.
before the problem can be solved.
Yeah, yeah. Luckily, hopefully it gets debunked, which definitely happened.
It happens eventually, yeah.
And then the research can continue.
Yeah. Yeah, maybe Charles?
Yeah, I've got a question. I noticed you didn't mention much about cellulosic biofuels. Recent work here and at Michigan State indicates there's enough cellulose that you can literally replace all crude oil, but it requires massive hydrogen inputs. And of course, you may or may not be aware of DG Fuels made that announcement of a $5 billion cellulose to jet fuel plant in Minnesota. I've known you're very quiet on that subject, even though it's the only one that might replace essentially most crude oil on the planet Earth.
Yes.
Or are you waiting for them to build the plant?
Well, there's the issue of the massive amounts of hydrogen and where it will come from.
Yeah, about 630 million tons globally.
Yeah, so that's a real problem, I think. But again, so here I'm being skeptical, right? And that's okay. I will say that I don't like to cut off ventures. I think that ventures should be, if people think they have a path to both profitability and scaling, I am all for trying everything because we need all possible solutions. I was humbled when I was asked by the National Academies to sort of be the intellectual Switzerland at a round table associated with biomass, the whole biomass to fuels supply chain and technology chain. And this was quite a long time ago, actually. And I was just stunned. I'm not a plant person. I'm not a biochemist. I do know what cellulose looks like. I will say, and the nice thing about cellulose is at least it has carbon-carbon bonds already, which is good. You don't need to remake those, right? But the amount of hydrogen, I think, is so daunting. And until we have a way, who knows? Maybe we will start prospecting geologic hydrogen in mass quantities so that there'll be enough to make it. But I'm going to reserve judgment.
Well, as you know, there's also the Exxon billion cubic foot a day hydrogen plant where they're going to sequester the CO2 in the Gulf of Mexico, the Baytown. And that's the scale you have to have. That's from natural gas.
I know.
You get another question in the back here?
Plants.
Yeah.
Yeah, thank you for the great talk. So I'm interested more on, climate policy. So we've talked a lot about more the engineering side, but I'm kind of curious. So, your title Inform has, 3 components to it, transformation, intervention, and adaptation. But I'm always thinking, or I've been thinking more, especially very recently, about what is the resiliency of our climate policy, and especially in the US, right? So, on Friday we saw a really big proposed budget cut for NOAA, DOE, NSF, all of this, right? And it's not just on the basic research, but for example, all of the NOAA programs, which were supposed to build resilience for coastal communities, for example, in the Northeast, are going to get cut or are proposed to be cut, right? But for example, if you look at countries like China, they're reaffirming their long-term plans for, their overall climate policy. So maybe could you comment a bit on how can we build in resilience in U.S. climate policy, and what can we do as scientists or as voters to kind of ensure that propagates upwards to actually become something tangible?
Yeah, it's a great question. Thank you. And it's something I've been very worried about. I mean, I didn't want the whole discussion to get hijacked by what's going on. I'm not saying you're hijacking, but hijacked by what's going on right now. But I am deeply worried because it feels like they're working under very different assumptions than certainly, lots of experts are working under. And one of the things in the report, in the reports that we generated for the National Academies last year and the year before, we talked about the need for certainty of policy, that there will not be investments made in the private sector if there isn't certainty of policy. And it is deeply unfortunate that there isn't that certainty of policy, and China has had, clear certainty of policy for a very long time. And the part that I just have a hard time with is I don't understand how they can say, the current administration can say that they want to compete with China, and a lot of what they're doing is disinvesting in such a way that they will not be able to compete with China. And so if you really want to compete with China on the national stage, on the international stage, you don't cut science, you don't cut engineering. They may cut other things, but that's the last thing you cut, because we know that research and development is what has led to the tremendous advancements that the U.S. has provided and has enjoyed. And you also don't cut, and you don't make people fearful of coming to this country. And so I think that we should be, we have been a country that has welcomed talent. And now many people are rightfully concerned about whether this is the right place to come. And I think that is going to harm very much the science and engineering enterprise. And then we won't be competing with China. So I don't quite understand the strategy. So what can we do? You can write to if you go to the American Physical Society website and look under their policy, they have a policy arm. They have a very nice way of telling you who your congressperson is and giving you a way to write to them directly about your concerns, and I think that's worth doing. They actually do pay attention to the number of letters they get, so I think that is important. And I think we have to recognize that for the next few years, we will need to find ways to engage states and the private sector in preserving science and engineering and work in these areas that the current government is not prioritizing. And that's what we'll have to do.
Hi. Thank you for the great talk. You talk a lot about stakeholders. I guess as we look into this transformation, intervention, and adaptation, what kind of stake do you think like very wealthy oil and gas companies have to hold in this, if any?
Yeah. Thank you. Because I have a strong opinion about this. I think that there's no way we should be demonizing these companies that have enabled our way of life. And the current Secretary of Energy is not wrong when he says that it has lifted people out of poverty, and he wants to do more of that. So I understand that. I think we should do both. We should lift people out of poverty. We should also recognize that we have, and this is, again, the philosophers taught me things, this concept of intergenerational ethics, which is a term I had not heard before. I sort of had already embodied that I used to say before I went to this participated in this workshop with the philosophers, that I wanted to know that at the end of my life, I could look back on it and know that I'd done everything I could to not leave the planet in a place where my grandchildren or my great-grandchildren were saying, what on earth were you thinking and why weren't you doing more? So coming back to the oil companies, we need to partner with them because they have expertise, especially in this electromanufacturing space. They have infrastructure, especially in the carbon dioxide removal space that I talked about. All of that, in building pipelines, et cetera. They have expertise and infrastructure that for us to say, no, you're too dirty for us to work with, we're going to start all over from scratch would be really ill-conceived. We absolutely need to partner with them and work together to get through this transition. That's my feeling.
Straight in the back with the mask.
Hi, thank you. So you brought up the electromanufacturing programs that you were talking about earlier, and one of the technologies you mentioned was joule heating. And I was a little curious is why you chose joule heating as opposed to heat pumps, because heat pumps generally are more efficient in terms of the heat transferred from electricity, but obviously they're more expensive and they require greater design considerations. So I'm wondering...
There may be things to do with heat pumps. I've just happened to be involved with a project that sends electricity through carbon felt that then onto which is attached catalysts. And so it's a way to essentially very precisely control over a very short period of time the temperature associated, well, I shouldn't say very precisely, but well controlled, and you can pulse it on and off the temperatures to which you're exposing the catalyst. So you can actually, really beautifully explore a kind of way of doing catalysis to make chemicals that hasn't been explored before. So it's just an example. But as I said, I'm agnostic to, I want all possible creative ideas to be explored.
I think we'll do the last question over here. Yeah, so wait with the microphone, please.
Yeah, thank you very much. So something I was always missing in the IPCC reports is a distinguishment of negative emission technologies from mitigation and adaptation. So what I do in my own research, and also apart from this, I tell all my students if they want to be ahead of the curve, and that it's a good time right now to look into all the negative emission technologies that exist. But something that I do is I make a clear distinguishment between adaptation, mitigation, and negative emission technologies. Is that a reasonable thing to do in your opinion?
Well, I mean, negative emission technologies is a subset of carbon mitigation strategies, right? And so I just think that needs to be made clear, right? And I agree. In fact, so full disclosure, at the end of the Obama administration, there was a task force that was tasked by the Secretary of Energy to look at negative emissions technologies, and I was a co-author on a report that came out right at the end of the Obama administration. And so those are clearly, for example, if you take CO2 out of the ocean or the atmosphere and you mineralize it, that's a negative emissions technology. I consider, in terms of carbon mitigation, mitigation also falls, anything you substitute clean electricity for fossil fuels is a form of carbon mitigation.
Yeah, that's exactly the distinguishment I wanted to make. So for me, it's clearly different to do ocean fertilization, let's say, or afforestation on one side. That's clearly like the category of negative emission technology, in my opinion. And then decarbonizing electricity and electrifying energy consumption.
Yeah, they're different, definitely.
Yeah. Thank you.
All right, so thank you very much. First, maybe let's thank Emily Carter again. And I just had a few announcements before we go. First of all, after the talk, we have refreshments downstairs, and if everybody could just go downstairs right away afterwards. Otherwise, we end up scattered between upstairs and downstairs. It's not so good. I wanted to advertise. We have a podcast, What If It Works? And I would recommend if you look at this QR code, you'll find all kinds of interesting information. This seminar series, MITEI Presents, Advancing the Energy Transition. This is the last talk of this academic year, but we'll be starting again next year, and we've already confirmed one speaker. On October 8th, we'll have the Vice President of General Motors in charge of sustainability and batteries come. So I hope you'll be able to join us then, and we'll have announcements of the other talks in the fall coming up soon. And finally, these kind of conversations are critical. As Professor Carter mentioned, really we need to have all the stakeholders involved, and we in the scientists and engineering community have to find solutions that are really going to work for people and going to figure out ways to make them work for all the stakeholders. And I hope that when you go out of here tonight, you'll feel energized to, talk it over with other people and try to figure out ways that we have to find real solutions that are really going to work. Otherwise, we don't have solutions. So get out there and keep working. Thank you very much.